difference in exotic potentials.
Alright, I did my research on the charge transfer between the perovskite and the electron acceptor TiO2. So for a little background, this is a picture that I drew to kind of explain how this is used. So the sun emits photons, which are these rays, to a solar panel, and this is a picture of what's happening inside the solar panel. So there's a sandwich between the hole acceptor and the perovskite, the TiO2, and then the electron, which is the electron acceptor. The perovskite has multiple layers, the unoccupied layer and the occupied layer. So the electron is excited from the occupied layer to the unoccupied layer, or the unoccupied level. This leaves behind an electron hole, which is shown in the red outline of the electron. Then the electron goes from the unoccupied layer to the electron acceptor, which then has a negative charge. The hole left behind by the electron has a positive charge. This is all sandwiched between two metals, which are connected by wires, which can be connected to something like a computer, which will charge the computer, which completes the circuit. This image was provided by Landon Johnson from his prior research. This is the 1D potential curve of the hydroxyl molecule that he'd worked on. And then this shows how the potential corresponds to where the molecule is. This figure shows the eigenstate energies on the potential curve. This section right here is the energy barrier that I'll be talking about later, just for future reference. And when you excite the electron from, when I go back a picture, sorry, something that I meant to mention on this slide. When you excite the electron from the occupied level to the unoccupied level, that gives it enough energy to overcome this barrier right here, which I'll show two comparing videos that I got from that later in the presentation. So the next 3 slides will be more about my methods that I used during the simulation. So this figure shows the probability versus time of finding an electron in the perovskite. So this graph was used to find the transfer rate. This section specifically, this linear section, was used to find the transfer rate in my calculations from the electron, or when the electron goes to the perovskite from the electron accepting TiO agent, which it's also called the electron hole recombination rate. This is a graph of the potential energy again that we saw before with all of the eigenstates, and then this red and tan line up here is the probability of finding an electron in the perovskite. Again, this section is the barrier, and at this initial momentum, this side over here is completely flat because there wasn't enough energy to overcome that barrier. This is the data that I collected in this table. So these are the initial momentums that I tried in atomic units, and then these were the transfer rates that I got from the previous probability versus time graph. The kinetic energy, which is not shown on this table, was calculated by squaring the initial momentum and then dividing that by 2 times the mass of an electron. And that kinetic energy was multiplied by a constant to find these temperatures. This K value is shown in inverse seconds, which is just the transfer rate here converted into inverse seconds by using the conversion that 0.02 electron volts of kinetic energy corresponds to 300 degrees Kelvin. This column is the natural log of this K. And then these 2 values here were put into the Arrhenius equation to find the activation energy, and so on, these 2 for this and these 2 for that, and going down the table. So a conclusion that could be drawn from this data was that increasing the initial momentum also increases the activation energy. This is the first video that I have of a comparison. So this video, the initial momentum was set to 0. I'll play the video and then I will explain. So it's a little slow because the MATLAB was taking a video and it made it slower, so it usually happens faster than this. But the reaction shows that when the initial momentum is 0, there's not enough of energy to surpass this barrier, which means there's no product that's produced. And then this is when the initial momentum was set to 1. And here you'll see that there was enough to surpass the barrier, and that over here there's the product produced. And then this is still showing the probability of finding the electron. Any questions?
Okay, let's thank Kaylin.
What is a reaction? You're talking about the product and the reaction, but you didn't show any chemical reaction.
Sorry, I was...
And what reaction you're talking about?
The electron going from the perovskite to the electron acceptor. Sorry, it's not really a reaction. That wasn't a good word to use. It's the transfer. Yeah.
So you are talking about electron transfer, hole transfer, right?
Yeah.
So you know the electron, what is the hole?
Where's the hole on this graph?
And what is the hole mean? I mean, physically, we know the electron particle, and what is the hole?
The hole is when the electron goes from the occupied, here I'll go back.
No, can you return back to your figure with showing the surface and the molecule?
This
Or
one?
whatever. Yeah, this one, right? You asking where the hole is located on a
Or
like what
system, or what is your question?
Or what is the definition of hole? I mean, what is this hole?
The hole is, so right here when the electron leaves the occupied state and it's excited to the unoccupied state, the hole is where the electron was, so that a new electron can be accepted.
Then how are you transferring the hole in this case?
Yeah, I'm not researching transfer,
Hypothetically,
sorry.
how the hole can be
How
transferred?
what can be transferred?
No, because it's just empty space, right?
Yeah.
Yeah,
So
I don't know how the hole could be transferred.
what happens at the low states? Are there any electrons below? So,
Yeah, so the electrons, I believe, would be excited into the...
well, technically you can imagine if there is something pushing the, or maybe if it's not the low state, then you probably have electrons above. So if electron takes this empty space from below or from above, then you create a new hole at the different level.
Right.
And this is what you can say that the hole was transferred from state 1 to state 2, right?
Okay.
So of course it's not hole which is moving, it's
Yeah.
electrons which going from one place to another way, and then your kind of vacancy
Okay.
is moving, and you can say that this is also transfer of the hole.
Okay.
I have chemistry question. What's perovskite?
Yeah, I probably should have given a definition for that.
Again,
but
return back to your slide with with this real structure.
this, oh, wrong.
And
This
it would be good if you
I
had some
believe
color
this
scheme
is-
for your, for different atoms. So
Yeah.
do you have any ideas what these colors for which atoms they stay for?
I know we talked about which colors were which ones. I don't know if I remember correctly. I know that this is the dye and this is the perovskite.
It's not dye, right? In this case, it's CO2, and this is
Or
your type.
sorry, not dye. TO.
It's titanium dioxide nanoparticle.
Yeah.
Titanium oxide nanoparticle. Yeah.
I believe there's.
Okay, I will help you. There should be what? There should be lead. There should be bromine or iodine, or what kind of?
I think it's bromine.
Bromine. So any idea? And something else.
Cesium.
Cesium. So now you just need to figure out which one is which one.
Okay. I think these ones are the bromine. No.
I don't know.
Do you know?
So the lead are the tan colored ones. The cesium are the blue ones that are kind of like inside of the cages, and then the bromine are the more reddish ones.
Okay.
So that's perovskite?
Yes.
Are there any other perovskites? What's the term perovskite is used?
Oh, it's a very wide term.
Yeah, I think it just means like the cage, like he kind of said. I don't know the definition, I'm sorry.
That's a specific type of the solid state with that unit cell.
What?
With that unit cell, you can have different perovskites depending on which metals you have.
Oh, okay.
So it's a type.
Like, for example, cesium can be substituted by some organic ligands, right? I don't know.
Sorry, what was it?
So, was it cesium? Oh, no, not cesium. Something can be substituted, but another cations coming from organic cations, right?
Yes, yeah. So methyl ammonium and lead iodide is another really common one. So instead of the cesium, you have like a whole ligand just stuck in there.
And again, bromines can be probably any other halides.
Yep.
And instead of lead, anything instead of lead? No?
Not that I frequently see, but you can. I know that you can, because I think I've seen, oh shoot, what was it? I may have seen titanium in place of the lead. Oh, just T? Okay, yeah, that.
But then the efficiency drops 4 times.
Yeah, but it's not quite as toxic as anything.
More questions to Kevin?
Just very quick question. So this is a three-dimensional structure, right?
Mm-hmm.
So what is the dimensionality of your potential has to be, and what you use for your simulation?
For the simulation, we use the 1D potential, but
Okay.
I think
So it's kind of a projection. It's
Yeah.
exactly the projection on this layer which you show. But in reality, of course, it has
right.
three-dimensional shape.
Yeah.
And very quick, another question: Can you go to your initial kind of state in a potential
This one? Or
where you show in the wave packet or whatever the electron? Yeah, this one.
this one?
Yeah. So you said that it's not enough energy to go through this right side, right? So what is the probability at the initial moment, right, before it's actually moving anywhere? What is the probability to find the left side? This side? Yeah. Oh, doesn't matter. Yeah. What is the probability to find the electron?
On titanium dioxide.
Ah, this is where titanium dioxide is.
Yes,
Yeah.
this is the titanium dioxide side, and this is the perovskite side. There's, I believe, no chance of finding it.
So
if-
zero?
Yes, if the initial
Sure.
momentum is.
It's electrons. Is the barrier infinitely large?
Yes.
Yes.
No.
It's there. You can see it.
Yeah,
Which barrier actually electrons should move through?
this one right here.
And doesn't look like it's infinitely large barrier.
Right.
So it's a finite size barrier.
Mhm.
So, have you talked about tunneling of electrons through the finite barrier? Particle in a box.
Yes, we did.
What is the difference between classical particle and the quantum particle in a finite size box with a finite barrier? If it has less energy than the barrier. Classical particle has no way to go through the barrier if its energy, initial energy, is less than the barrier energy.
But the quantum particle would.
It can penetrate because your wave function has exponential tails, which makes not zero, it's a very small probability, but not zero probability that your electron will be outside the finite barrier. So means if you wait for very, very long time, of course you will see some electron density on the other side of your potential.
Okay, so are you saying
But
that?
initially it is zero because initial state is prepared this way, right?
Well, it depends how you prepare. Well,
it takes time.
at a very initial moment, if it's really just localized.
So she was right.
But no, when you're solving the equation, right, your wave function should have this exponential tails, which immediately make your exponent is not having exactly zero at any x, right? Which means you will not get zero probability.
Okay, so just very, very small.
Very, very small.
Okay.
Anyone else wants to challenge Kevin with questions? If not, thank you for watching. We have next presentation about translational motion of electrons in